Introduction to Metabolism. And this is a background theory. We won't get into the details of metabolism just yet. We just want to look at some of the theory behind it, why it happens, look a little bit at energy, and then we can get into some details of how it actually happens. So here's a nice diagram of some of the metabolic pathways that happen during a cell's metabolism. Lots of different things incorporated in with metabolism, but essentially we're taking one thing and we're turning it into something else for a particular reason. And sometimes that reason is to get energy out of it. A lot of times what we're going to focus on is getting energy out of it. Sometimes it's going to be storing energy or converting one thing to another thing, but many different metabolic processes, and all of them involve changing one thing to another for a particular reason, and some sort of energy change is going to go along with that as well. You can think of the reason why metabolism happens in the way that it does is because these are biological systems. Nothing can be made anew. It is always based on what was previously there. So you end up with this reusing of previously existing systems to get the job done. And this can lead to some very complicated pathways that seem like they are unnecessarily complicated. So you can think of it kind of like a Rube Goldberg machine, and these were comics drawn by this guy that basically showed a simple change being done through a very elaborate process. So here's an example of a self-watering palm tree where essentially the goal is to water the palm tree, but it involves a ridiculous series of steps that will eventually get the job done. It starts with something and it ends with the desired goal, but it seems quite elaborate to actually go through this entire process. And this is a way of thinking about metabolism. We are starting with something, we are ending with what we want, and there's this long, complicated process that we need to go through to get there. And the reason why we have these processes that seem sometimes overly complicated is because they are being inherited from previously existing processes. And so you can end up with some extra complications to them that work perfectly, right? Otherwise they wouldn't be around if they didn't, or near perfectly. And so this is why metabolism can be somewhat complicated. So looking at energy itself, every one of these changes is going to involve some sort of change in energy. And so we want to make sure we're talking about the same thing with energy. Essentially, we're going to think of energy as the ability to do work. And so when we use that term energy, we're thinking, okay, well, that means something can be done with that energy. There's kinetic energy, which is for us, we're essentially thinking of as heat. So that's the movement of the molecules. And more specifically to metabolism, there's potential energy, which is essentially the storage of energy within different particles. So we'll have these different particles, and they can have within them, stored within their bonds, potential chemical energy. First law of thermodynamics is that energy cannot be created or destroyed. It can only be converted. So when a cell needs energy, it's going to have to get it from somewhere else. It's always this process of taking energy from one place and using it or moving it to another place. We're going to be using chemical bonds to get our energy, and so essentially chemical bonds are going to be broken. And when we break these bonds, we're going to be building other bonds with that, and we're going to couple those two processes together, and this is where we're going to see the energy. If you want to break those bonds, it is going to require an input of energy. But if you couple that with a formation of other bonds, then you can get the process done. The attraction of an atom's electrons towards another nuclei will result in chemical bonds. So just a quick chemical overview. When you have an atom and another atom, they can share electrons between them, and you have sort of a coexistence of those electrons between the two atoms. That's a chemical bond. So for a nice simple molecule, you can imagine hydrogen gas. This bond that we draw here, that's the shared pair of electrons, and essentially they're going to be stable like that. If you want to change that level of stability, you've got to put in some amount of energy. You could move them close together, but we're not going to do that. We're going to be breaking them. And so if you want to break that bond and separate one atom from another, so you get these two separate atoms, you've got to put in some energy. So again, this is energy here. They're stable in a bond, and if you break the bond, you've got to be putting in energy. So always you have to put in energy to break a bond. But the opposite is true as well. If you have unbonded atoms, you can then get them to bond together, and in doing so, they will give off energy. So breaking bonds takes energy, forming bonds gives off energy, and we can actually tie those two together. That looks like an X. Imagine tying those guys together, and that will allow us to get stuff done. So again, summary. Do not forget, despite what some diagrams may lead you to believe, breaking bond takes energy, forming bonds releases energy. Sometimes the diagrams don't show the entire process, but there's always those two steps involved with it. So if you wanted to burn methane, you've got to actually put in energy, and you know burning methane gives off energy. So it's a two-step process. First, the energy has to go in to break up the particles, and then maybe when they reform, you might get out more energy than you put in. For sure, you're going to get out energy. The question is, did you put in more energy or did you get out more energy? With the burning of methane, we know that we get out more energy. So you start with methane and oxygen, you put in some energy, and we get carbon dioxide and water, which means we've got some energy out of it. And there may be a difference in what you put in and what you got out. And that is the extra energy in this case. We're actually giving off some energy. The initial state started here and the final state started there. So there is a change in energy. We're actually releasing energy by doing this process. And again, we're always going to release some energy and we're always putting in some energy. The question is, what is the difference between those two steps? We can refer to this as an exothermic reaction. There's a little bit more exaggerated change in energy. If you start at this energy level and you end at a lower energy level, then the change between them is obviously going to be, you've lost energy, it's gone down energy. So this exothermic process gives off energy. Now remember, it's always two steps. You always have to put in some and then you get out some, and then the difference between them, that will determine whether it is an exothermic process or an endothermic process. Again, if you start with something, you have to put energy in to get it to change, but you may get some energy out of it. And if you put in more than you get out, that process is called endothermic, and essentially that energy that it's using to get there has to be derived from the environment. And so endothermic processes and exothermic processes both involve input and output of energy. The question is, what is the net difference? If the net difference involves giving off energy, then that is an exothermic process, and we see energy given off. If it involves a net consumption of energy, because the products are more energetic than the reactants, that is an endothermic process. Activation energy is the term that we use to get the process going. Wherever you start, you've got to put in some energy. Whether you start high or you start low, you've got to be putting in some energy. That is referred to as the activation energy, the energy required to break the bonds. The difference between them gets the symbol delta H. It's the change in what's called enthalpy, but the change in energy is good enough for us. And it is the difference from where you started to where you ended. And again, you could have a decrease in energy, and that's an exothermic because the system itself, the thing you're talking about, has lost energy, and so that would be a negative delta H. Or you could have a positive delta H where it actually started low and went high, and that is a endothermic reaction that would have a positive delta H. So endothermics have a positive change in energy. They've taken some energy from their environment, now they have it within them. An exothermic reaction is a negative change in energy, or negative delta H is another way of saying it. This thing that is created that's temporarily there but not there for very long is called an activated complex or a transition state. It's what you get when you've broken the bonds but not yet formed your final products. All right, important term here. The second law of thermodynamics is saying that when you transfer this energy, so you can transfer energy all day long, but when you do it, you're going to lose some. You can't have a perfect transfer of energy. There's always going to be some that gets lost. And entropy increases when this happens. So this term entropy, let's try to get roughly the idea of what it means. Essentially, if you think of entropy as being disorder, that's probably a good enough way of thinking about it for us. When you want to get something done, you need to have the energy to do it. So we can refer to this as free energy. So it is the idea that if you have some energy somewhere, you can use it to get some process done. We can use the term free energy to do that, the ability to do work. So you can imagine if you have something that is highly ordered, you could take it and make it disordered. And in doing so, this disordered way of being is less useful. You can't do as much work with it than you could with your highly ordered initial state of being. That is essentially what entropy is when you have something that you've changed in a way that lessens the ability to do work. That is an increase in entropy. So this brings us to spontaneity, it would be the term, I guess, whether a reaction will happen on its own or not. And it has to do with that free energy, and it has to do with that entropy. We'll look at the details in a minute. But essentially, we want to know, is a reaction, is this change going to happen on its own, or do we need to put work in to get it to happen? So for example, you never have to worry about a giant ball rolling up a hill towards you. I was going to be rolling down a hill toward you. It's not that you can't move a ball up a hill, but you have to put work in to get it to happen. It does not happen spontaneously. It will roll down a hill spontaneously, but it will not roll up a hill spontaneously. Same thing happens for reactions. Iron will rust on its own. You don't have to do anything. It'll just do it on its own. It is a spontaneous change. If you wanted to do the reverse process, if you wanted to like smelt iron from iron ore, you can take rust and you can turn it back to iron, but it is not spontaneous. You have to put in a bunch of work to get it to happen. And the same thing is going to be happening with all of our biological reactions. The calculation to figure out whether this will happen on its own or not uses this idea of free energy, and sometimes referred to as Gibbs free energy. But again, free energy, the ability to do work. We can essentially look at, okay, if you had something and you turned it into something else, you've changed it. Did that change increase its free energy, or did it decrease its free energy? That's the question that we're asking. And then we can say whether it'll be spontaneous or not based on what that change has been. So we won't do the calculations, but essentially it involves these three factors. Remember our delta H, this is essentially the change in heat energy. This idea of entropy as to whether you're making the system more ordered or less ordered, and then temperature also factors in through this equation here. But if you look at a particular change, let's say turning A into B, you can look at the three factors associated with that change and you can decide, okay, is this going to take work or is it going to happen on its own? Is it going to be spontaneous or not? If the calculation works out to give you a positive delta G, that means it's not spontaneous. That means you've got to put in work to get it to happen. If it is a negative delta G, then that means it will be spontaneous. It's sort of happening on its own. You don't have to put work in. So think non-spontaneous reactions, they need to be supplied with work. You have to put work in. And here's the terms that we're going to be using. We're going to sort of summarize that up in two ways. And we're going to say, if you have to put work into it, if it's not going to happen on its own, it is an endergonic change. If it does happen on its own, if it is spontaneous, based on all that stuff we just talked about, it is an exergonic change. So biology depends on these two processes being tied together. If you want to get something done, you need to tie in a process that is going to give off energy with a process that requires the energy. Because if you just have the process that requires the work, the energy, it's not going to happen. It's just going to sit there. It's not spontaneous. So what you have to do is you have to tie together a spontaneous reaction with a non-spontaneous reaction. You get the spontaneous reaction to run the non-spontaneous reaction. And this is how biochemistry works. So metabolism is the transformation of energy and matter through the use of those metabolic pathways that we saw at the top. Very elaborate, complex set of systems, but it is always tying together a spontaneous change with a non-spontaneous change. We've seen catabolism, breaking down compounds. This generally is going to be releasing energy. So if you tie that together, you can get an anabolic process to happen, the anabolism, the building up of things that does require energy. And again, as long as you tie these two processes together, you can get them to happen.